So the next theme will be about lignocellulosic thermoplastics. So what is this all about? Well, the title will tell you a bit. It's about components of wood using lignin and cellulose and creating sustainable kind of plastics that you can actually melt and form. So you can actually have shapeable materials created from forest raw materials that are meltable and can be molded into different shapes. So perhaps screw corks on bottles or interior design in your car and other advanced geometries. So the question is, can we replace plastics with forest raw material? Well, let's take a look and see how far we have gotten in research like this. So let me just stop my sharing and introduce our first set of speakers, which will be postdoc Mikael Reed from KTH and industry supervisor Emma Östmark from Stora Enso. So please go ahead and start sharing your screen, and they will talk about understanding the interactions within fiber composites. The floor is all yours.
Okay, great. So I think we could start. Mike and I will tell you a little bit about the collaboration that we have between Stora Enso and KTH. It is called Understanding the Interactions Within Fiber Composites. And as I said, it's a collaboration with Stora Enso, and it's Mike at KTH who is the postdoc that is conducting the study. And I will start with the background and some of the purpose of the study, and then I will hand over to Mike, who will give a little bit more on the details on the project. So next slide, please. So a little bit of background. This is the next generation of eco products that we want to develop to replace plastics. So consumers, they're looking for products that can enable them to lead more eco-friendly lives, and they want to minimize waste, the carbon footprint, and also reduce the use of plastic. You all know this. So strong brands can meet these demands and prove to consumers their ambitions and progress towards a circular economy. So Stora Enso in early 2020 launched Pure Fibre by Stora Enso, which is a new selection of formed fiber products. And this is a type of composite, and formed fiber products are designed for their intended use and can either be used and then recycled or composted after use. So Pure Fibre is a product that can tell a story of an eco-friendly circular brand. It's made of you can see some examples to the right. They are hot pressed and can achieve most 3D shapes. They have, on average, wood fibers, and are also sustainable and food safe materials. They can also be, as I said, recyclable in cardboard stream. I hope you can hear me. I see that you're losing my voice a bit, but I would try to be as clear as possible. Next slide, please. And Pure Fibre products are formed fiber products, and they are manufactured from various chemical pulps, for example, CTMP, and they're made by hot pressing into a desired shape in a molding machine. So the raw material is pulp, and it's made from wood from FSC and PFC certified traceable sources in Sweden and Finland. And Stora Enso is manufacturing the raw material, the pulp fibers, and at our mills in Sweden and Finland. And we do the converting at Hylte mill in the southern part of Sweden. The initial annual capacity during the pilot stage is about 50 million units of products, but of course we want to expand this in the future. Next slide, please. So then we come to this postdoc project. What we want to do at Stora Enso is to get a better understanding of the processes. So we do this together with KTH. And there we are working with modeling, and the interactions of the formed cellulose fibers is modeled. And we use tailored cellulosic filaments that can be used in conventional adhesion characterization techniques. So we make these filaments and model them, and then we get some kind of results of the adhesion. And Mike will go into this in a while. And the aim is then also, when we have all this data, to scale it up to imitate the macro scale processing at a later stage. So this was just a short introduction to this, and now I will hand over to Mike.
Thanks, Emma. That was a great introduction for what I've been working on in the last couple months. So I'm a postdoc at KTH in the Fibre and Polymer Technology department under the supervision of Lars Fibres. So within this project, what we want to try and understand is how better we can improve the fiber-fiber interaction within paper and board products. And so when we start to consider the mechanical properties of these materials, it ultimately relies on the individual fiber strength as well as the fiber-fiber joint strength. And so the challenge that we're facing within this is that cellulose fibers are largely heterogeneous, and it can be difficult to handle them because they're relatively short. So if we look at some SEM images of pulp fibers, you can see that there's a lot of different hierarchical structure that we have in here, and they're rather non-uniform. And so if we take a closer look at these structures, we can see that there's a lot of different materials on the surface and different types of morphologies that make it challenging to model these systems effectively. And of course, this all depends on how these fibers are processed, either they're chemical pulps or kraft pulps. And there's a variety of things that need to be considered when we're trying to look at the fiber-fiber joints. And so if we want to understand the individual fiber-fiber joints, it can be difficult to make these structures and measure them effectively. And so what we want to do is build a model system in which we can mimic a variety of different types of fibers and include a number of different types of modifications to see how we can improve these fiber joints. And so the process that we've chosen to do is to make model filament fibers. Some of you may have seen this before, but we use a flow focusing system where we have cellulose nanofibers along the core and HCl on the outside of an extruder. As we extrude this material into an HCl bath, the CNFs coagulate and form a fibril. So down here in the bottom left, we can see a video of an extrusion process. We have a variety of different extruders available, either 2-barrel or 3-barrel, and we can add different types of functionalities within the system. So the example shown here, we have P.P at assess in the system so that you can see the fiber extrusion. The great thing about these fibers is that I believe they model fibers more effectively than a classical dissolved cellulose. The CNFs are made of aligned cellulose 1-beta fibrils, so this is a better model compared to a dissolved cellulose structure, which doesn't have the same crystal structure. So what we want to do is then take these filaments, dry them down, and try and use these to make individual fiber-fiber joints so that we can measure the effect of different types of additives, either wet or dry strength additives, or adding different types of functional materials into these filaments. So when we're starting to look at our filaments, we have a variety of data. We have SEM images where we have filaments after drying that are about 30 to 40 microns in diameter, which pretty accurately reflects a typical pulp fiber. If we look at it in a little bit more detail, we have a line cellulose material along the axis of flow of these materials. And if we look at the surface of the filament, we can see that we have the wrinkling that we would expect to see on cellulose fiber. If we look at the Young's modulus, we can see that we have a Young's modulus of about 18 gigapascals and an ultimate strength of about 250 megapascals. So we believe that these are good model systems for what we can expect from a variety of different types of pulp fibers. So the main project, or the main goal of this project, is to make fiber joints, and that can be a little bit challenging. To make these fiber joints. So we have a couple of different options. We can extrude our filaments and join them together in the wet state and have them fuse together, or we can dry them first and then make fiber joints. So if we're thinking about making them from never dried filaments, what we can do is take our filaments and suspend them between two supports and then touch them together and use capillary forces to link these materials together. You can see on the right here, this is what the result is. We can see we have this Y-shaped joint where we have individual filaments that have been joined. But if we look a little bit closer in the SEM, we can see that these filaments actually fuse together and become one uniform filament. So when we go to start pulling these materials apart, it can be very challenging to get them to peel apart right at that joint. And often what results is that when we peel them apart, we have one of the branches break. So from this quick study, we can see that in order to model fiber joints effectively, we're going to dry the filaments before we make the joints. And so that's easily done. We can dry the filaments together, or dry the filaments, and then simply hot press them together to create these fiber joints. And so this is an example under polarized optical microscopy. We can see here where we have the aligned fibers going in the bottom left to the upper right and oppositely in the other direction. And if we take a look in the SEM, we can see that we have a similar joint made in the SEM. And so a couple things to note is that when we hot press these filaments together, they compress and flatten out as you'd expect for a regular fiber joint. And we can very accurately measure the interfacial area between these joints. And so if we look a little bit closer at the joint specifically, under the microscope, we can see that we have aligned fibers in both the X and the Y directions. And we can characterize how they're aligned within the joint using the polarized optical microscopy. And we can look in a little bit more detail at the joint using scanning electron microscopy. So if we look at the polarized optical microscopy here, we can see that we have within the joint, the alignment changes during pressing or following pressing. So with the filament that is moving from right to left, we have a uniform alignment, but when it gets into the joint, we see changes in alignment of the cellulose fibrils. So that allows us to kind of understand what's actually happening within the joint. The other nice thing about this technique is that we can actually measure the interfacial area between the joint and use that to understand how effectively these individual joints, the strength of these individual joints based on interfacial area. So if we look at a little bit closer in the SEM, we can see that we have individual CNF filament fibers that have been included in the joint, and some of them have actually been pulled apart. So we have enough adhesion between these two different filaments in order to pull apart individual CNF fibers. So there's a lot more to be looking at, and so this is the early stages of the development of this project. And there's a couple of next steps that we want to achieve with this work. And so one is that we want to increase the scale of production. So we can rapidly make CNF filaments. We extract them at 30 centimeters at a time, and then we can make a number of different joints. But what we wanted to do in relation to the fiber composites is determine the best conditions in which hot pressing leads to the strongest fiber joint. The other thing that we'd like to do is then determine what kind of modifications that we can include within the filaments to improve the joint strength. And that can range from adding different types of polymers, different types of hemicelluloses, and a number of different other types of small molecules. What we can also do is determine when we add these materials in. Do we add them during the extrusion process, or do we want to add them after we've done the drying and maybe perhaps use a layer by layer modification to improve the joint strength? Next, what we're going to be doing is working with people at Solid Mechanics is to develop a testing rig for these individual fiber joints. They're rather small. They're about 30 microns in diameter. So the Instron is not necessarily the best tool to use to measure the individual joint strength of these fibers. And so that's where we are with this project. We're really excited to move forward and really produce a number of these joints and help us understand the mechanisms that are going on within these molded fiber composites. And so with that, I would like to thank you all for your attention. Thank you to KTH and my group, Stora Enso, and everyone here at Treesearch, and we'll be happy to take any questions.
All right, thank you so much, Mikael and Emma, for a great presentation. Now, actually, we have a bit of twist in the program just to keep you a bit awake. We have a joint presentation, so we will have a number of speakers joining into this presentation. And we're experiencing a bit of problems with showing the right person at the right time. We don't know if this is due to lag or what it can be, but we will try to show the faces of the people that are actually talking. So we will have Industry Supervisor Jan Wahlberg from Tetra Pak with the two projects presented by postdoc Emil Engel from KTH and postdoc Alexander Mehadzinski from Linköping University. Then we will have Industry Supervisor Niklas Kvarnlöf from Billerud-Korsnäs, followed by postdoc Nasmun Sultana from Chalmers. So let me stop sharing that for you, and you guys can just go ahead and share your presentation, and we will try to make sure the right person is on camera, but let's see how that works.
Yeah, okay. So this this project here, it's basically around a material which is called amore, which is a thermoplastically modified cellulose, and it stands for amorphous oxidized and reduced material. The two companies involved is Billerud-Korsnäs and Tetra Pak, and Billerud-Korsnäs is doing the material production and say the upscaling and all the things involved with the synthesis of the material. And at Tetra Pak, we intend to look at how we can produce with the material. We have the three postdocs, Nasmun, Alexander, and Emil, who are all three working in different areas. Nasmun mainly with Billerud-Korsnäs, and then Alexander and Emil with us at Tetra Pak. Okay, next slide, please. So our interest, the Tetra Pak interest for this program, is that we see that sustainable materials are needed worldwide, but we will have different solutions for different markets. In Europe, the Single-Use Plastics Directive, or the SUP, is very much controlling what we can do and what possibilities we have to use different materials. But that differs from other markets in the world. So we need basically different solutions for each market. The collaboration with academia is something which we strive for, and we find it's a very, very interesting combination that we have the basic research done at the universities, and then we have the implementations for these products that they, or these materials that they produce. And we have found in the making of the amore material, which has been going on for very many years, we saw that having a common goal, saying that we should use and explore these materials is very useful, but we should not have a fixed road. We should not say what we should come up with. We should see what we do come up with. And that is very, very interesting way of working. And I think that's a functional way of working. What we need in industry is, of course, not micrograms of these materials, but we need kilograms. And for that reason, the upscaling of these materials and the technology is very, very important. And we see that we can do this by a knowledge transfer of how this is done in the lab scale, and then by collaboration we can move it out to the industry and that scale that we need in industry. Okay, that was about my presentation of why Tetra Pak is interested in this.
Thank you, Jan. So, as Jan has mentioned, there's a need to shift to more sustainable materials. And with policy directives like the new Single-Use Plastics Directive, we are interested in looking at modified cellulose fibers as a possible replacement for existing thermoplastics. And specifically in my project, we're interested in the use of extrusion and injection molded modified fibers for the preparation of complex shaped parts. So we have identified dialcohol cellulose fibers as potential replacement or application for extrusion and injection molding. They're prepared by simple two-step process of pyridate oxidation to convert the C2 and C3 hydroxyls to aldehyde groups, followed by total reduction to prepare the dialcohol cellulose. In the SEM images, you can see the unmodified fibers which degrade before they melt, as we know. And then on the right, you have the modified fibers converted to 31% degree of modification dialcohol cellulose, which is softer and less crystalline. And this behaves in a thermoplastic manner. Our understanding of the thermoplasticity of this material is based on a fibril level core shell model. Because the reactions are done under heterogeneous conditions, what we end up with, we think, is a crystalline cellulose core within the fibril, surrounded by amorphous dialcohol cellulose shell. And on the right-hand side, you can see materials that have been prepared by melt processing. So at the top, you have 85% modified fibers and 20% low-density polyethylene, which has been injection molded to prepare bottle caps. And below, you see a sort of proof of concept of the extrusion of 100% modified fiber material. And when this material is soaked in water, re-wetted, you can see that the wetted material resembles a fibrous soaked material. So we believe we maintain the overall fibrous nature, fibrous structures. And so our scientific question in this project is, how do the material properties and the processing parameters affect the melt-like processing of these modified dialcohol cellulose fibers? And then our strategy is quite straightforward. So we will prepare chemically modified fibers to varying degrees of modification. So in the SEM images, you can see the 31% degree of modification material, and also a sample of material that has been converted to 46% degree of modification. And even at high degree of modification, you can see that the fiber-like structure remains intact. Well, the material softens, and you can see some spreading out on the surface that is a result of that modification. The modified fibers will then be melt processed, and there we will control parameters such as water content and the temperature of processing. We know that the water content of this material has a major effect on the glass transition temperature. And so with higher water content, the TG is reduced. And so we would like to find some kind of optimum water content and also good temperature at which to do the processing. And once we obtain the processed material, we will also do characterization. So we will characterize the modified fibers before processing, and then the processed material afterwards. And we will use a variety of advanced techniques. So we will analyze the morphology by SEM and fiber analysis. We would like to use tabletop sacks and wax, and then a variety of the techniques to analyze how the TGE and other thermal parameters change. So DMTA and tensile testing. And we also plan to do melt rheology mainly at the rheology lab at Chalmers University. And I think now we'll hand over to Alexander, who will talk about his project.
My name is Alexander Mechanjewski, and I'm a postdoc in Linköping University. And particularly, I'm working in the laboratory of organic electronics. Today, I want to give you a brief overview, basically, of the project that I'm just starting. I'm supervised by Igor Zudenko from our group and Christian Muller, who is his group is also working on these materials. So a bit about the simulations that I'm doing. I'm working with molecular dynamic simulations, and just a few words about the people who are not so familiar about these types of simulations. These are simulations which are based on classical physics. And so basically solving Newtonian equations of motions, where we have the forces of atoms are basically derived from, can be derived from experiments or quantum mechanics. So we have a good representation of the interactions between all the atoms and the molecules in our system. And particularly, we are looking really into the molecular interactions between cellulose nanocrystals in this project and polymers, particularly about the polyethylene acrylic acid. Here we can have a fundamental insight from molecular simulations in order to give some guidance and understanding of some questions which are still left from the experiments. Here I'm just starting with very simple, with for example this one cellulose nanocrystal, which is depicted here on the picture on the top, which is surrounded by a polyethylene acrylic acid, and these are the different, these are the specific simulation parameters that we're working on. Next slide, please. And what we are aiming to achieve in this project, and how in general we can connect these simulations with the experiments, is, for example, as I said, we can look really into the detail and into the microscopic picture of these materials. And we want to see how are the density of this polymer, for example, around the CNC, and what are the surface interactions between the CNC surface and the polymer. We also want to see how these nanocrystals can self-assemble in the EA matrix, because this is a very important question in order to understand these materials. And also, for example, we can measure very accurately the interactions between the individual fibers, crystals. And this also can be connected to, for example, flow properties which you measure in the lab. And also we can, for example, want to look what will be the minimal amount of acrylic acid co-monomers which are able to disperse these CNCs. And in this way, we can also do system predictions and try to give guidance from this fundamental perspective into the inputs to the experiments. Next slide, please. And as I said, these composites, cellulose and polyethylene acrylic acids are really interesting materials. They are thermoset-like plastics, which can be recyclable. So it is really interesting and relevant materials for nowadays economics. It is shown that by just introducing cellulose into these polymers, we can have a drastic increase of the melt stiffness and the resistance of the formation in the melt of these polymers. For example, here on the right, you can see this is a picture from the experiments where we have the neat polymer on the cellulose polymer matrix. And this is mainly, we think this is because of a formation of dynamic cellulose networks, which can reform and adjust during heating and cooling. However, of course, there are several open questions that are left from this study. For example, this study is done in Chalmers from Anna Pedersen. And this open question that we would like to try to answer from molecular dynamic simulations is, for example, what is there a different density variation around the cellulose nanocrystals? And also, what is the predominant interactions in this polymer matrix? Is it a cellulose interaction, or is it the cellulose and polymer matrix interactions? And we also want to have a look about, as I said, what will be the minimum amount of the acrylic acid comonomer which are able to disperse the CNC. And I'm really excited to start this project. I mean, it's already started, so we're in the beginning, and I'm looking forward to work on this project. Thank you. And now I think we go to Nazmon.
Yes, soon we will go to Nazmon, because first we will go back to the industry from the academia. I can just... So, hi, I'm Niklas Karnlöv, developer engineer at Korsnäs. I will give you a point of view from a company towards this type of postdoc program initiations. And by the way, the headline here is our main goal for this material, actually. So we see, how do you get a new product out? I mean, it's quite a simple process in theory. You have the idea and you present it to other people that thinks it's a good idea and give you resources and time for this, and you go for the research this idea. You look at everything that you can, you test things that you think are good, and optimize parameters and stuff like that, and finally you get out a perfect recipe, you think, and you head over to the factory for the implementation, and they say, oh, it's okay, it's very good, and you get out the amazing product. So it's a real straightforward and easy process. But yeah, let's look at our case. Well, we have the idea. We would like to do or produce papers of high ductility by modify fibers, and we think that, yeah, that's a good idea, and people also think that, yeah, you can go ahead with that because we like that idea. So we have done a lot of research and are doing a lot of research and the parameters and everything. So that's very nice and dandy like that. But of course, when you run over to the factory, you get a cross for that. Here's the breakage of the chain, of course, and you can see your amazing product fade away into the future, long time in the future. So of course, between the research and the product, you have huge implementation hurdles to get over. And here are some examples of those. I mean, the scale up itself, what equipment should we use? How large should they be? What type of materials should we use? You have a chemical and product handling. I mean, you go from grams in laboratories to kilograms and even tons. And how should you handle it, and how should you store it, and how should you take care of it? You could have buildup of byproducts which you can't see in the labs, which could be a nuisance in the factory. Could have scaling of pipes and everything like that. Maybe you have very expensive chemicals, so you have to look at the recycling of chemicals to use it over and over in the factory. You have a lot of waste materials maybe that should be taken care of, etc., etc. for that. So the research to the product is a very hard thing to get by. So here we see Treesearch as an organization that could be like a link for handling these type of problems, is what we can see. And for this type of projects, the postdoc projects, that could be a little part of solving these type of problems. And in our case, we're looking for the recycling of some chemicals for the production of the material. And the ones who's doing all the work, she's sitting at Chalmers in Gothenburg, and it's Miss Nazmun Sultana, which will soon deliver some clarification on what she are doing for us. So take it away, Nazmun.
Thank you, Nicholas. Hello, everyone. I'm Nazmun Sultana, and I'm working as a postdoc in Chalmers under the supervision of Professor Gunnar Westman. Now, the picture in this slide sums up what I'm doing. That is scale up of sustainable production of dialdehyde cellulose and dialcohol cellulose. Now, it is well known that peroxide oxidation of cellulose gives dialdehyde cellulose, and its subsequent reduction gives dialcohol cellulose. Now it has seen that dialdehyde cellulose has numerous properties, like it has excellent barrier properties, it is biodegradable, it is economically feasible, and most importantly, it is thought that it can replace petroleum-based products in the industry for barrier properties. So we are looking into that. Whereas dialcohol cellulose has excellent ductility properties and it has high possibility of thermoforming and melt processing. Next slide, please. Now, as I mentioned, that dialdehyde cellulose seem to have excellent barrier properties. So it is quite evident in the slide. The picture we have at the top, we see that it is of cellulose, that is normal pulp, and we see fibrils of cellulose strands, and it is just stacked one upon another in a very haphazard manner. Now, after oxidation, we seem to produce the dialdehyde cellulose, which I previously mentioned has good barrier properties, and that you can see from the picture in the left-hand side. You see a droplet of water on the material produced by dialdehyde cellulose, and we see that the water does not penetrate. The photo was taken after 1.5 hours of dropping the water droplet into the surface of DAC. And in a closer look, we see that it forms like a lotus leaf droplet of water, and this is at the down is the dialdehyde cellulose surface. And we see that it is very hard to penetrate it. On the right side, we see the picture of the same images of dialdehyde cellulose. And we see that there's a network formed, and it is quite a dense network. And so it inhibits the penetration of water or any solution into it. So we feel that it's quite a nice product to be used in barrier for packaging materials. Next slide, please. Now, what's the problem is that during the oxidation of cellulose to dialdehyde cellulose using peroxide, we produce a lot of spent periodate. Now that we don't want to just dispose in water or in the nature. So we have to come up with a nice plan to eradicate it. Now what we know that there has been a lot of research going on for the regeneration of periodate, like electrochemistry with ozone, but we would want something which can be implemented in the industry, as Nicholas said. So I have here used sodium hypochlorite. Now, when sodium hypochlorite is mixed with the spent periodate water from the industry in a specific amount and in a specific pH, then we see it reacts to form insoluble precipitate of sodium paraperiodate. Now, which when dissolved in a suitable acid, it forms the solution back, that is the sodium periodate in solution, which can be used again to oxidize the cellulose to dialdehyde cellulose. Now, this have been tried in the lab for about 3 times, and we successfully produced dialdehyde cellulose from cellulose. And in the FTR spectrum, you can quite see that there is a peak over 1732 centimeter inverse, which depicts that, okay, dialdehyde cellulose have been formed from cellulose. And the dialdehyde cellulose, which was formed while the regenerated pyrrolite, had a degree of oxidation of 30%. Also, this could be tuned, like various factors which affect the degree of oxidation, like time of oxidation and temperature of oxidation. So it can be tuned accordingly, so that it can be this DAC can be used in both billerud korsnäs and for Tetra Pak. So we can form accordingly and modify it accordingly as the need of the company or the industry. Next slide, please. Now, it is important that now what has been done is that regeneration has carried out in numerous processes. What has not been done is that to scale up the process. Here we have tried to scale up the process. You can see in the pictures that we have used in a very large scale, that is 5 liters. And you see the precipitate in the solution, and then this precipitate is just in the bottom of the vessel. The huge vessel has been used. So we have done this in a large scale, and we are quite confident that we can implement in the company and in the industry. You also see a same picture of the dialdehyde cellulose produced from the regenerated periodate, and it is quite similar to that produced from the fresh periodate solution. So we can conclude that it has been it can be quite efficiently used for to scale up the process and to produce dialdehyde cellulose from regenerated periodate. Now we are looking into the various factors. We are trying to optimize the factors like temperature, time, and various other factors that influence the formation of DAC and the quality of DAC, so that we could produce DAC in a very efficient way with according to the company standards, not harming the nature, and we are trying to do this. So I feel quite confident that we can produce DAC in a sustainable way, in an economically feasible way, and we are trying to better it every day to fit into the company standards. Thank you. That's all from my side. Thank you for listening, everyone. And for more questions, you can contact the persons in this slide. Thank you.
Perfect. Thank you so much to all of you. That was a massive presentation. Nice of you to have such a good collaboration going. I'm happy to hear that. So let's move on to the discussion. So Anastasia again.
Yes, hello, can you hear me?
Yes, we can hear you and I can see you at least.
Great. Thank you very much, everyone. Great presentations. And let's move on to the questions. So maybe we can start with the questions to Mike. Mike, are you here?
Yeah, I'm here.
Okay, great. So, so we have a few questions to you. And the first question is from Artem Kolachenko. And basically, Artem is wondering that the joints that you show are presumably from the dry state. Do you have the comparison from the wet state to get the idea how the shrinkage contributes to the joint geometry?
That's a great question. And so we use dry filaments to make the joint, but prior to joint making, we soak them for at least an hour to re-wet them in order to make the joint. So we take dry filaments, re-swell them, and then make the joint with the hot press. And so looking at how they change when they re-wet, from preliminary measurements, the filaments don't swell significantly when we put them back into water. So we're looking in that a little bit more detail and looking how water penetrates the filaments and changes the alignment of the filaments. But right now, we don't see any significant changes.
Mm-hmm. Thank you very much. I hope, Artem, you got the reply to your question. The next question to Mike is from Jakob. So Jakob is thanking you for your presentation, and he's saying that the way we have filaments to test the joints is really great. And he has two questions. The first one, is the surface roughness important? And how the surface roughness impacts your model system? CNF size, charge, water content after spinning, drying, kinetics. So maybe let's start with this question, and then I can move on to the second question of Jakob.
Sure, those are all great questions, and they're all like super important. The roughness, I believe, will play a significant role because you were going to be limiting the amount of contact between the filaments by having a rough surface. So what we found, however, is following hot pressing, the filaments become much more smooth and they flatten out a little bit. So we believe that we're actually improving the amount of contact area following the pressing process. And in terms of the spinning parameters, these all play a significant role, and we're doing our best to be as consistent as possible. All the filaments are dried under tension, and we're maintaining the same surface charge on all of the filaments we're making. That's something that we can tune, and we're looking into with the guidance of Stora Enso by changing the amount of hemicelluloses in there, what kind of CNFs we're using, charge content. These are all things that we're looking at.
Yes. Yeah, it's indeed very important. Thank you, Mike. One more question from Jakob, and it's related to the changed fibril orientation in the cross polarizer. And he's wondering, how are the fibrils organized in the model Fibre as compared to a hierarchical fiber of elementary fibril in macro fibrils? And how much would you estimate that could impact the fiber-fiber joint interaction?
Right, so within our filaments, the majority of the CNFs are aligned along the axis flow. So much like a regular fiber where largely all the cellulose chains run along the fiber length, that's similar. However, you know, there is a twist within fibers and things like that. That's much harder to model and mimic. But what we plan on doing is taking the fibers and making a variety of joints at different angles. So from a 90-degree cross and changing that angle to see how we can better model these systems and more accurately represent the variety of fiber joints that are within a fiber network. And so the alignment plays a significant role. All of these things are important, unfortunately. So we're trying to be as consistent as possible and looking into as many things as we can in order to get a good understanding of the individual fiber joints.
Great, good luck with it. It's a really fascinating work. And
Thanks.
then Gustav Lindberg, he also would like to ask you a question. So I will unmute Gustav's microphone. So let's see. Gustav, are you connected now? Yeah?
Yeah.
Great.
Okay, hey Mike, great presentation.
Thank you.
So I have a question. It was about the stress strain curve you showed.
Yes.
Was that for a reinforced fiber?
That was just for a regular filament that we had made. So our model filaments, we just put them in the Instron and just hold them.
Okay, so that was, okay, so it's not reinforced.
No, just a regular solid filament.
Okay, but so do I understand that you have a method for reinforcing the fiber? So increasing, like say, the yield limit, strain to break, and Young's modulus, and so on?
Potentially. We have a 3-barrel extruder in which we can make hollow filaments. So in that sense, we could include, for example, a more stretchable polymer or something along those lines within the core of the filament, which could potentially increase the yield stress or Young's modulus or something like that. We have a variety of pathways to make different types of functional filaments as well as reinforced filaments. So it's early stages. We've made a couple of filaments with good properties, but it's definitely something I'm happy to look into.
Okay, that's really interesting. Thank you.
My pleasure.
Thank you very much, Mike. I think there are no more questions to you so far. So let's move on to the next presenter who got the questions. It's Emil. Emil, are you here?
Yes, I'm here.
Great. So Emil, you got a question from Jakob. So he thanking you for a great presentation. And so basically he's saying that he wasn't aware that fibers can be made through the melting. And now he knows, which is great. And he has two questions in a connection to the core shell model that you presented. And that in your presentation suggests that an intact ribbon of crystalline cellulose can be observed. So how reliant do you judge that model? Especially as fibers are inhomogeneous with pores, can that lead to inhomogeneous diffusion and reaction rates? And then basically he's also wondering about the fiber source. Are they 100% cellulose or may contain any hemicellulose or lignin?
Okay, there are a few questions.
Yeah.
So the fiber source is bleached kraft pulp.
Mm-hmm.
And as I understand, it doesn't contain any lignin, it contains some hemicellulose.
Mm-hmm.
And in terms of the model, I don't think, so firstly, I mean, we were careful to describe it as melt-like processing. We don't melt the fiber completely.
Mm-hmm.
And so the model doesn't necessarily kind of envision a ribbon, an intact long ribbon of crystalline cellulose. It could be tending from a ribbon towards rods at higher degree of modification. And an important point on this in terms of understanding what is happening is that at very high degree of modification, we reduce particle size, so there's fiber shortening. And there are also some groups that have reported at high degree of modification by the same process, they obtain what appear to be dialcohol cellulose nanocrystals.
Mm-hmm.
So I think that it's probably something that tends towards rod-like portions of intact crystalline cellulose surrounded by regions of amorphous dialcohol cellulose, not necessarily a long ribbon.
Mm-hmm. Thank you so much. Can you comment also about his question of the inhomogeneity with the pores and how it can lead to the diffusion and reaction rates? Do you have any opinion about it? If the fibers are inhomogeneous and with the pores?
Yeah, I'm not really sure. I mean, of course, there is variability in terms of reaction rate. I'm not sure if I can answer exactly how, but yeah, of course, we're working with an inhomogeneous material, and something that is tricky is trying to obtain consistently the degree of modification targeted because of that. So all kinds of sets of parameters need to be controlled: stirring rate, the rate of addition of the reagents, and yeah, that can definitely affect, and certainly the type of pulp that you're using to begin with has a huge influence on the reaction rate.
Mm. Thank you very much, Emil. Good luck with the further investigation and development in your research. I would like to move on now to Nazmun. Nazmun, are you here? Nazmun, can you please unmute your microphone?
Yes.
Yes, okay, great. So we also got a couple of questions to you. Let's start from the first question from Atanu Kumar Das.
Yes.
So he's wondering if you have checked the difference in contact angle between DAC treated CNF and LCNF.
No, I have not, but I would really do that. We are trying to now find a best material with the best barrier properties, which suits both the companies. And after we find a product, we are definitely going to see the contact angle and for the barrier properties. Yeah.
Mm-hmm. Great. Then one more question to you, Nazmoon, from Pegah Hanjani.
Yes.
And so he's thanking you for the PPT slides, and he's wondering how dialdehyde pulp can increase the barrier properties, and what are the mechanism behind of that comparatively to unmodified pulp?
There is modification when there is oxidation of cellulose to dialdehyde cellulose. So the aldehydes in the fibrils, they form a network structure which imparts that barrier properties. So that's behind the modification.
I see. Challenging. So one more question to you, Nazmoon, from David Califano. He's thanking you also, and he's wondering, what do you think the reduced water absorption is only due to the desertification of the DAC network? Densification yes. Of DAC network. Or do you think there is an influence of chemical changes in the chemical structure and increase in hydrophobicity, for example?
Yeah, I just answered him. Yeah, the thing is that after the modification, there is network in the structure, and it depends, the degree of oxidation depends on various factors like time, temperature. So we can tune it into different factors. So the hydrophobicity and also the barrier properties increase or decrease with this tuning. So it depends actually. That for a lower degree of oxidation, the barrier properties are not so fine, so they don't show so much of hydrophobicity. But when there is a high degree of oxidation, you produce more materials. And also there is a difference between untreated and treated fibers. When the fibers are treated with sodium, and then they produce, I have seen that they produce a much denser network. So it depends on what factors are there. So it improves the hydrophobicity and also the barrier properties.
Thank you very much. So you got some more questions. Let's see. Yes, we have a couple of minutes still. So we have a question from Adriana Svensson. And she's wondering, how are you going to regenerate hypochlorite to make the process sustainable?
Yes, okay. Thanks, Adriana, for the question. As I said, that there are different ways, and researchers are looking into different ways to produce regenerated periodate for different things like electrochemistry and ozone. But for industry, when you see from the industrial perspective, then this is not possible. So I would like to use a thing which is cheap and which can be used in there in the industry, like sodium hypochlorite. As I said, it is very cheap. It's much cheaper. It's half the price of sodium peroxide. So now it has been seen, I have seen in different researchers that they have used sodium hypochlorite, but there is, degassing of toxic elements. And if some else is given, like some else acid is given to dissolve it, then you build up products. So we won't want that either. So I am now striving on to my best and trying to find a way and to optimize the things and to find a suitable acids, so that there is no degassing of toxic elements or toxic gases. There is no buildup of materials. So we are trying to make this process on and on, so that this process can be at least used for like generations. If we add a little bit of a catalytic amount of sodium periodate, then you don't need to throw it into the nature or into the water bodies, anything. And this process goes on, and we get our desired quality of dialdehyde cellulose. And so I think it would make a sustainable one.
Great. Okay, very last comment from Pega. He is thanking for your response immediately. And he's also wondering how the aldehyde groups make those network in comparison with hydroxyl groups. Is there any specific interaction, hydrogen bonding, and what is the degree of substitution of your dialdehyde cellulose?
Well, the degree of substitution I haven't recorded. I have only, because the companies are only interested with degree of oxidation, and a specific degree of oxidation is needed to work with the product for both Billerud Korsnäs and Tetra Pak. So I haven't looked into the degree of substitution. But when it comes to the aldehyde groups make those network, I just know that there is modification and there's a deeper part of chemistry, that if there's a hydrogen bonding or not. So I think I would look into it, and maybe my supervisor would explain it better than me. Yeah.
Thank you very much, and many thanks to all participants.
Yeah, thank you, Anastasia, and thank you, everyone. We have reached a point where we will go for a short lunch break. Not that short, it's 1 hour. So during this time, we will still have this webinar open, so you can still post questions. You won't see me on camera. I'm, of course, away for lunch. So a big thank you and a round of applause, of course, to all the panelists that joined in the morning, and to Anastasia, and to Per working here with the technical support. Any more support you need, just remember to ask us in the Q&A or in the chat. So now we will go for a lunch break, and after lunch we will listen to lignocellulosic energy applications. So at 1:15 o'clock you can just log in using the same link again, and we will be able to stream.